Yeah, thanks, Payman. Since Payman talked about ultra-wideband, I want to take a little bit deeper dive into the capabilities of ultra-wideband. So my role here in Cisco is mostly on evaluating new technologies that actually go into the access point and building and making proof of concepts. So ultra-wideband's capability of toward interpositioning is actually great. So here we have downlink TDOA, which is basically how it works is we have an initiator access point, and then we have some responder access points. The initiator access point sends a pull message to the nearby access points, and the nearby access points respond to those messages. And the phone is actually passively listening to those messages, and it can compute the position itself. So think about a GPS receiver, which is kind of like not transmitting any message to the satellite, while it is listening to the satellites and it is able to compute the position. So this is the beauty of downlink TDOA, that we can have as many as infinite devices which are trying to find their positions. So I have a 1-minute cool demonstration on indoor wayfinding with an Android app. So let's watch it and then discuss further.
Indoor positioning and asset navigation have never been more seamless. Leveraging the ultra-wideband capabilities of Cisco Wi-Fi 7 access points, we enable precise indoor navigation and asset tracking with sub-meter accuracy. In this demonstration, I'm using an experimental application on an ultra-wideband enabled Android device. The application retrieves the indoor floor map and other essential data from Cisco spaces, allowing the device to accurately determine its location by passively listening to inter-access point communications. This technology enables thousands of users to navigate large indoor environments such as airports and shopping malls without placing additional load on the network. Through an API call to Cisco Spaces, the application can display the real-time location of my backpack, which is equipped with an ultra-wideband tag. This is visually indicated by a solid blue circle. At Cisco, we connect everything, building the bridge to possible.
Yeah, so that was all about downlink TDOA. Since past several years, Cisco and Google have been collaborating with each other on exploring different technologies which are available for indoor positioning. So 2 years ago, we were testing with Google. We were testing fine timing measurement over Wi-Fi in the University of British Columbia. So we got a lot of attraction, and 2 years down the road, now we are exploring ultra-wideband. So we have Roy here on the call, positioning, and he can further explain the key concept behind the downlink TDOA.
Thanks, Rabe. So yes, I'm just going to give a very brief deep dive as to what you have to do on the phone in order to position the phone precisely using UWB. So if you recall on the previous slide, Rabe described the messages which are being sent between the initiator and the responder access points, serving as UWB anchors. And basically, the messages are designed in such a way that you can calculate the effective time of arrival of those signals at the phone. And that means between any two of the access points, you can calculate the time difference of arrival. Now, it turns out a time difference of arrival signal represents a hyperbola. So time and space are related by the speed of light. So basically, if you imagine a map, as you can see in front of you with the 4 access points on, we can now draw hyperbolas of constant time difference between those devices. And where those hyperbolas intersect is the point where the Android phone is. It's made a little bit harder in that the hyperbolas don't exactly intersect in the right place. So actually, we have to use a little bit of high-level math. We have to use a weighted least squares solution in order to find out where that position is, or at least the best estimate of that position, which of course with ultra-wideband is very accurate. And that's what we're relying on for a set of applications.
So where's that calculation done? Does the phone report the time? How does that work with, and then the infrastructure, does the phone calculate the location? Does the infrastructure provide the map to the phone? How does that work?
Yes, yes. So the phone does the calculation. It receives the messages. It calculates the arrival times, calculates the time difference of arrival, and then applies that math in a location engine to provide that exact spot that you're seeing there on the screen.
So the location engine is embedded in the phone.
Correct.
In this case.
Yes,
Okay.
that's correct.
Okay. So the map or the AP locations themselves have to be provided to the phone in some way or another.
Yes. So you can think of this in two ways. One, you could write an application based on an API, which we're in the process of developing and releasing. It's very close now. So this could be a dedicated app which already has all the maps associated with it for that particular building that you're in. Maybe it's a retail environment where you're showing that this app is part of a big box store retail application. And so it has the map, and then it will figure out the positions of the access points, and then it will calculate the position of the phone and then show it as a dot on the map, and then perhaps give you some navigation capabilities across the map if you're looking for a particular product, as an example.
I have a follow-up question, Roy and Al, to that. So is this a particular model of phone and or software of a version of Android, or what do we need there?
Yes, so the phone has to support UWB, so that there has to be hardware on board. And
Yep.
at the moment, typically the pro versions of Android phones support it. So you find this with Samsung and with our own Pixel phones.
Okay, thank you.
Gotcha. Interesting. So that also helps with sort of the latency, right? Because all the calculation is done right there.
Yes,
So-
it helps with latency. It also helps with privacy, because the advantage of downlink time difference of
Correct.
arrival is that only the phone gets all the information. So only the phone can calculate its position. So the user app has control over who knows its position. Now, it may be that the user app will advertise that position itself, right, back to the cloud service. So if you're part of, say, a big box store loyalty app, that you may have agreed to share your location with the store. That's your choice. But ultimately, the phone has the control over who gets that location information.
Oh, that's fascinating. Yeah, that's a great point. I hadn't thought about that. I'm sorry, Ray. I didn't mean to hijack that. It was just, this is really interesting.
Yes. Well, actually, it's a great intro into the next level of discussion about applications for precise location, which is what UWB positioning gives you. So we've talked about navigation in a store. So the top left, maybe a typical store plan. We want to find a product on a store, and we navigate directly to that product. And if you have enough accuracy, your product may only be a 3 or 4 inch item, and we can position you exactly in front of that item where it is on the shelf. And so that would be a great user experience to take you all the way, if you're in a hardware store, to that little plumbing gizmo that you've been looking for. We could take you right in front of it and not have to alert a store associate to find that item. So I think it'll be a great user experience in its use. And then there is the other side of the story in retail, and that is the store associates themselves need support. So, for instance, we've learned that a lot of the store associates will occasionally misplace or lose their scanning devices, the devices which they carry around. A lot of them are Android-based, and so that particular scanner can be reporting its position back to the central server, which is managing the database, and it can then, on a query of where's the device, it's been lost, can then provide that information. Another application for store associates is related to online shopping. So when you shop online for, say, groceries, there has to be some guy who walks through the store and boxes all those groceries for eventual delivery to you. And you want that process to be as efficient as possible. So ideally, you would have the list. You calculate the shortest distance between all the items based on traveling along the aisles, and then you can then create that plan for the picker, as they call them, to travel that route and tell them where they are or when they've arrived at the item, and basically make that all more efficient. And in the case of a store that has a lot of people inside, so a busy store, you can also have several pickers operating simultaneously, and you can figure out the best route to avoid the congestion in the store. So I see this as a mechanism which stores providing online services like this can be much more efficient and avoid congestion, and it'll just be a better user experience and a business proposition for everybody.
We had a couple questions here. There was a question via YouTube here about, do all the APs need to be reachable by the phone? So I guess what are we looking at as far as like APs, number of APs that we need to, be within quote unquote earshot of the phone?
Right.
And
Yeah.
maybe what's the cutoff there?
Well, I'll defer the question to Payman's part of the talk,
Sure.
because he'll talk about AP density. But yes, you do need to have a critical number of APs before you can calculate a position. So that's certainly the case. Now, in a moment, I'll talk about the fuse location provider, and you'll see that maybe the ultra-wideband isn't the only thing which is providing position. So we can also fill in some of the gaps with other technologies. Okay, I also just wanted to tie in asset management with indoor location aisle level positioning. So the other big issue, or if you like, contention point when folks are managing assets in stores is that usually there's no, in a big store, there's no sort of warehouse concept. Everything is put out on shelves. But the problem is, if a big order comes in, you may not have all the shelf space to put the item where you expect to put the item. So typically the excess gets moved around stores and gets put in places that perhaps traditionally you wouldn't expect it to be. And then, of course, that location is forgotten about, lost. So the location of items which are placed on shelves can be determined by scanning the object as you put it on the shelf. And the scanner knows its position, it knows its ultra-wideband position, and that position can then be stored in the database. So not only do you have the positions, all the items which were in the expected position, but you also have the unknown positions as well. And my understanding is that this kind of problem occurs in warehouses all the time. And something like this with precise indoor location will facilitate accurate asset management in a complex environment like that. Now, to tie this back to Android, I talked a moment ago about having an API for ultra-wideband positioning. To use an API like that is a complex task for, say, a programmer. They have to come up to speed on a number of math algorithms in order to calculate position. So Android typically simplifies that process by having a very simple location API called the Fuse Location Provider. So this is a location which the vast majority, or an API that the vast majority of people use, and basically they ask for a location, you get a location back. And the way this works is that we hide a lot of the complexity of the underlying location technology from the developer and from the user. And what we do is literally in the name, we fuse the positions, if available, from a technology such as GPS, clearly when you're outside, cell tower signal strength, Wi-Fi RSSI and Wi-Fi RTT round trip time, and the IMU. And as we're developing the UWB API, the next thing that we'll add to the Fuse Location Provider in the relatively near future will be the UWB positioning capability. So when UWB is available, Fuse Location Provider will start using the UWB signals in order to calculate the position. And all of this information is pulled together in a single algorithm, and one location is generated with an error circle around it, an estimation of the error, which can then be used to judge, how accurately you can show something. So you might, for instance, be showing a snap to aisle map if the accuracy is, say, within 1 to 1.5 meters. If it exceeds that, you might just show you're in a general location inside a store, perhaps because the store doesn't have any special location technology other than, if you like, traditional Wi-Fi with only RSSI available. So that's how we use it, and that's how we'll expose it to users. And so in some senses, it may become invisible to the user, which at some level is also, a very good thing that nobody has to really worry about this. We'll take care of the complexity. And then finally, I'd like to just sort of reemphasize the 911 location services support. So if you're not familiar with this, when you make an emergency call on an Android phone, we have something called ELS services, emergency location services. So there is a requirement that phones will deliver their estimated position when an E911 call is made. But the cellular service providers only have a limited ability to determine your position. So the accuracy can be quite high. And if you're sending emergency workers to help somebody out, perhaps they're trapped, there's a fire, so on, it's important they get there as quickly as possible. And if there's error, then you're putting lives at stake. So Android has worked with the emergency services and has produced additional information which gets added to what the cell providers give the dispatch centers. And this all gets fused together in some sort of report that's given to the dispatcher. So in other words, the better we can locate an Android phone, the more accurate information we can give the dispatcher in order to send the emergency workers to the right place and hopefully save lives. And of course, UWB will be one of the technologies which improves this even further. But we do a pretty good job now, even with conventional Wi-Fi, compared to what the cellular providers produce.
Hey, Roy, quick question. On that top right corner, of course, I recognize the most of those, but there's one called IMU.
Yes, IMU stands for Inertial Management Unit. And basically, it's a catch-all for all of the onboard sensors that the phone has, which can help provide a position. So the accelerometer, the gyro, the compass. And of course, those technologies allow you to create a relative position. So as an example, you might use it because when you're outside, you have a reasonably good GPS fix of where you are. But then you go inside, it is possible the building you're going into doesn't have any other technologies. The Wi-Fi satellites are no longer visible. But now you can use your step count and your direction in order to, from that position, to calculate your new position. And of course, at some point you might encounter some Wi-Fi access points, and then you can reassess your position. So this is how we're switching between technologies. We're fusing the output of these different technologies together, including the sensors and the IMU.
We have a question that came in as well on the asset management or asset tag use case here. And I think the answer is probably it depends, but hypothetically speaking, how long would the battery of a tag last, for example, using a technology like this, and how does it implement power saving features and capabilities?
I'm going to hand this across to the Cisco guys because I think they have more direct experience.
It depends on many factors. It depends on how frequently the location of the tag is updated. So, these tags send messages. Rabe will show how they work, and the frequency of those messages will say how much power they consume. This other factor is how large the battery is. We have asset tags with the small batteries and industrial asset tag with very large batteries. But if you go with, not too high of a frequency and a standard battery, some of them, last easily 5 years.
Okay. And just to be clear on that, what you mean by frequency is, as the user, can I control, or maybe the administrator, can I control how often that tag is checking in?
Yes, you can absolutely control it. We have a way to program it. And then the other piece of it is a lot of these tags have motion sensors in them. So
Sure.
if you're sitting in a place stationary, they don't send an update. And when they start moving,
I see.
they send update, they stop moving, send update, and then they don't send update. So the more intelligence we put on the tag, the less power it consumes.
So while we're talking about tags, it sounds, after talking to Roy about how we're doing this with Android, it sounds like these are fundamentally different, right? So the tag obviously is not downloading the map and computing the locations in a tag, right? How does the tag work versus how does the Android phone work? Sounds like they're kind of two different. The end result's the same. I get a location, but it sounds like they approach it from two different ways.
Yeah, I can take that question. So
Okay.
basically, phone works on downlink TDOA and computes the position, while we have uplink TDOA for the tag side, where our cloud has the position. Or there is a way that phone can directly communicate with the tag so that we can navigate to the tag as just like the demonstration that I showed earlier. Now, what we mean by asset management, there could be different use cases. Imagine you have an Android scanner app, which is a device with ultra wideband capability, and you scan an item in a warehouse in one of the gates, and you have like your warehouse has like tens of gates. Now, when you scan it, the Android device with UWB has its very accurate location. Now, it can record the location of the scanned item, and when it moves further, so when it is scanned again, the location will get updated. So these are some ways that we can invoke for asset management using downlink TDOA and uplink TDOA.
But tags are very simple. So tags are very simple devices. They cannot compute the location. They don't have maps.
Yeah.
So with these simple devices, Cisco Spaces, is the place we compute the location of the tag. The APs receive the signal. They do some computation, send it all to Spaces, and then we compute. And we have BLE and UWB tags. So yes, they're fundamentally different technologies. Well,
Yeah.
it's like the same technology used fundamentally differently, right?
And the cool
Right.
thing about these location technologies, which are not RSSI based, like Wi-Fi FTM and ultra wideband downlink TDOA, is that the phone would have the floor level information as well. So imagine someone is making a 911 call, so the 911 response team would exactly know where the person is and what floor he is on. So look how cool it is. Like he can have a very fast response time if he has
Yeah.
this.
Yeah.
Speaking of the E911, there was a question actually that came in via Slido on this, and it's basically like asking if there's any more details on this E911 integration. Will Cisco be providing or publishing a reference guide on this? Lots to think about and lots of regulations with telcos.
Yeah, so I would ask Roy to take that question. So this is basically on the Android side. Maybe Roy can speak more about it, how Android processes the location and sends it to 911.
Yeah, so there's a protocol which allows an Android phone to talk to a server that's provided by the cell service operators, and that protocol is well defined, and we can put a lot of general information in there, and that happens in parallel with the information that goes, the more basic information that goes over the cellular link. So that's how the information gets to the provider. Then in terms of the phone knowing its exact position, there are a number of factors which come into this. Then in order for the phone to calculate its position, not only does it need to know the TDOA information, but it needs to know the positions of the anchors, which I think perhaps is more of the root of your question. How does that information get there? And that ties back to Paiman's comments about the product which Cisco have, which is AnyLocate, where the access points themselves can figure out the location information and send or provide that in something called LCI, which is location configuration information, which then gets delivered during ranging processes, particularly with Wi-Fi, but a similar version happens with ultra-wideband as well. So in other words, during the ranging process, we get that extra information which calculates the position of the phone, and that's the thing that we deliver to the dispatch center.
And I think fundamentally this question comes from at Cisco. We've always the locations always kind of come from the network, not from the device. And so the question is, how does the network provide that E911? In this case, because the phone's actually calculating that value, it can provide it directly. And so it takes that requirement off the network to actually have to provide that. So that's an interesting another interesting perspective in this model, right? So
yeah. And it is a collaborative thing, if you like, between Android and Cisco in this respects, because if that LCI information, location information, is available in the access points, then the Android phone will make use of it. But if it doesn't have that information, then its ability to calculate the precise position is much reduced. So in other words, the two companies together are actually providing a mutually supportive capability for E911.
Right. But fundamentally, the protocol of the communication to E911 is now from the device itself, which makes it, and that's great because it doesn't matter where the device is. If it moves out to GPS or whatever, the device then owns that. So yeah, that makes a lot of sense. Interesting. Oh, there's a lot of things I hadn't put two and two together till we've had this conversation. It's really interesting. So,
and we're talking a lot about location here. I know on other episodes we've talked about analytics. Magisha asked another question here around analytics. For example, this could be used for analytics, right? Airports could see what passengers or what routes they're taking through airports. Companies could get population stats per room, and this is more along Cisco Spaces, I think.
Mm-hmm.
Yeah, and there's actually a lot of potential for accurate indoor location across several sectors like airports, as you mentioned, shopping malls, campuses like the universities, where students are having campus tours early in September every year. So in fact, in a few weeks period, we will be exploring downlink TDOA with Android, and the University of British Columbia will be running some early field trials. So maybe we can have some follow-up episode on that sometime later.
Yeah, and I'd just like to emphasize that this issue of infrastructure finding the position, or even analytics, right, of individuals. This is a sensitive area, and we understand this is sensitive. So I think any of these applications where the phone determines its position, the user will then have to decide whether they want to opt into analytics. So there will be some sort of screen that will pop up which say, are you happy about anonymizing your location and sharing analytics, which will help us improve the efficiency of the store or the airport or whatever it is. And I think if you do that, involve the user and explain what you're doing, then it becomes a lot more acceptable to people who might see this as a concern.
Agreed.
Cool. I think now we can touch upon uplink TDOA for asset tracking. So basically, on the downlink side, we are computing the position on the phone that can be used for indoor wayfinding. However, if we want to track our assets, we can use UWB asset tracking, where we have a small UWB tag that's short and that sends a blink message to the nearby access points. Since each access point receives the message at a slightly different time interval, we can leverage uplink time difference of arrival to compute the position. So all these measurements are sent to Cisco Spaces, where we have UWB location engine that we run, and then we leverage 3D rich maps on Cisco Spaces to showcase the location of the tag. I have a small 2-minute demo video on asset tracking, so let's watch it, and then we can discuss further.
Accurately locating people and assets indoors remains a challenge. Traditional methods using Wi-Fi or Bluetooth often fall short in dynamic or cluttered environments. UWB offers a powerful alternative, enabling precise, low-latency positioning down to the sub-meter level. From real-time asset tracking in warehouses and hospitals to worker safety and wayfinding in large campuses, the use cases are rapidly expanding. Here's how it works. A UWB tag transmits a blink message which is received by multiple access points. Using uplink time difference of arrival, each access point records the precise time a signal receives. By calculating the differences in arrival times, the location engine triangulates the tag's exact location. This technique is robust, fast, and energy efficient, making it ideal for mobile tags and real-time updates. I have a device with the UWB tag attached to it. As I walk, the location is updated in real time on 3D rich maps in Cisco Spaces. Notice how smoothly and accurately the location follows the actual path, even around corners and in open spaces. The tags come in different form factors. The tag can be worn, attached to equipment, or embedded in devices. Applications like indoor navigation, security, and smart automation become possible now in environments where GPS fails. With UWB, precise indoor positioning is no longer futuristic. It's here, it's real, and it's ready to scale.